Hey, what's up, guys? This is Chung here again. So this time, 1,793 maximum score of a good subarray, right? So you're given like an array of integers, right, and the integer k, okay, and your task is to find a good subarray, right, whose the score is maximum. It's maximum. So what is the score? Score is basically is the is the minimum value, right, within this subarray, right, multiplied by the length of the subarray, right? So for example, we have these numbers here, and the k is equal to 3. So the k means that the subarray has to contain this k's element, right? So for example, this one actually the biggest one we can get is the biggest score we can get is 15, which is this one, this subarray, right? And then the k, this is k is 7, right? And then for this one, the minimum of this subarray is 3, right? So, and the length of this subarray is 5. That's why we have 15 for this one. And then second one here, right, so it's 20 because, k is pointing to here, to this one. So in this way, in this example, we have, there's no way we can go left, right? So we have to keep going to the right, right? And then for this one, it's obvious, right? The biggest one is 20, right? 4 times 5, which is 20. And here are some constraints, right? So the length is 10 to the power of 5, right? And k is in the same range. Cool. So I mean, to solve this problem, I mean a naive approach would be like n squared, right? Basically, we try all the possible subarrays, right? And then we calculate the minimum numbers along the way, right? And then we just basically try all the possible subarrays which contains this this case element, right? But that will TLE. So for this one, for the maximum values here, we have some options. Maybe we can try think of like the binary search, right, or the DP, or greedy, right? But for this problem, I think it's kind of obvious that there's no DP idea here, right? Because whenever you move you move to any left or right, the minimum value will change, right? So which means you cannot use DP. So to solve this problem, actually a greedy or the binary search, they both work. And even for so for the binary search, actually it's using the same greedy idea, right, within the binary search. So in the end, so this problem is a greedy problem. So what does the greedy idea is doing here? Basically, we start from this case element, right, which is 7, and then for this one, basically at each of the place here, right, we have two options. We can either go left or go right, right, and we always go to the direction which has the higher number of value. So which means for 7, right, we have 3 on the left and 4 on the right. So which means that for a size of okay, so I think here's a proof of this greedy here. So we have a size, okay, so we have a size here. So at the beginning, size is 1, right? So basically the minimum possible score of a good subarray is the maximum score for the size for the subarray within the range from 1 to n, where n is the length of numbers, right? So which means that if we can efficiently calculate the max score, right, for each of the sides or for each of the length of the subarray, right, then we can just do this. We can just also get the maximum score out of the sides from 1 to n, right? So basically, this greedy approach is telling us, every time if we follow this greedy approach, we have size 1, 2, 3 until n, right? If we're using this greedy approach, every time when we expand to a bigger size of the array, that array is will definitely have the biggest max score within all the subarrays who has the same length, which is okay. So for example, if also that the subarray also has to include this k, right? So for example, if we are 7, right? So 7 is a size 1 subarray, right? So for this one, the max score is 7. Okay, and then for the size 2 subarray, right? So for size 2 subarray, we have two options here, right? So we have 7 3 and 7 3 7 and 7 4. That's the two options, right? And it's obvious that 7 4 will have the higher score comparing to 3 7, right? So which means that for size 2 subarray, we have 7 3. Sorry, we have 7 4 in this case. So how do we get to this 7 4 state, right? Basically, we move to the right side because 4 is greater than 7. Sorry, 4 is greater than 3. Okay. And so how about 3 here, right? So for all the size 3 subarrays, what's going to be the max score for that? So basically based on our greedy approach, we are saying that the biggest the subarray can give us the max score of size 3 is 7, 4, and 5, right? Because for size 3 subarray, we have how many options we have? I think we have 4, 3, 7, and then we have 3, 7, 4, and then we have 7, 4, and 5, right? So those are the three options, right? That can include this 7 here. So as you guys can see here, this one will give us the biggest answer, the max score, because we are getting the minimum. We need to use the minimum value within this array to calculate the length. If the length are the same, right? Then if the length are the same, then the only factor remaining is we just want to get the biggest. We always want to go to the direction that has the bigger number, so that in the end it can result to a bigger minimum number in the end, right? Because if with 3 and 4 and also 3 and 5, right? Whenever if we go to a smaller size, then of course when we reach the size 3 here, we'll definitely have smaller a score the score here. That's why this greedy approach works. Basically, so the greedy approach is saying that every time we're as long as we follow the greedy approach, every time when we reach a new size of a subarray, we can be sure that subarray will give us the max score for all the subarrays who has the same size here, right? And then we can simply do this one from 1 to n, and then we among all this kind of scores, if we get the maximum one, that's how we can get the final answer, right? So now I think it's clear that we just need to start from the case location, and then we try to expand to the left, either left or right, right? And then along the way we maintain the minimum values, and also we calculate the final answer at the same time. Okay, cool. So as long as we can figure that out, right? I mean, the code is pretty straightforward. So we have a left and a right pointing to k here, right? And then we have the answer. So at the beginning, the answer is size 1 subarray, which is the k, right? The nums k here. And then we're going to have a minimum. minimum numbers at the beginning is also like a nums k, right? And then we have n dot length nums, right? So, and since we could have only it's possible that we can only extend to one side, right? So that's why I'm handling this in this way. Basically, while left is greater than 0 or right is smaller than n minus 1, right? And then I do this, so I check if we can expand to both sides, right? And then I can compare the values. Otherwise, I simply just go to the side that allows me to extend, right? Or to grow. So if we can expand to both sides, we compare if the left one, the L minus 1, is greater than the R plus 1, right? If it is, then I know I will go to the left side. Right, and then the minimum will be minimum of nums L, right? Else we do R plus 1, and the minimum will be the minimum of nums R, right? Else, right? I mean else if L is greater than 0, which means that, so now this one is saying that we cannot go right. We can only expand to left. In that one, we just need to do this one, right? And else is the other side, right? So we copy and paste this part here. Okay, and then every time we maintain the answer, right? It's going to be the max of the answer dot the minimum, right? Times what? Times the length of the array, which is the R minus L plus 1. Okay, and then we simply return the answer. Yep. If I run the code. Okay. Oops. Oh, here. Or, right. Yep. So passed, right? So I mean, obviously the time complexity for this one is O of n, right? Since we're using a two-pointer techniques here, and time complexity is O of 1, right? We only have 2 pointers here. Cool. Yeah, I think that's pretty much it is, right? So for this problem, I mean, I think it should be not that hard to figure out the greedy approach. I think a bit tricky part is that how can you prove that, right? I mean actually it's always tricky to prove the greedy approach, but fortunately for this one, I think I think at least we can prove that by assuming, right, by proving that every time if we follow that greedy approach, at each size of the arrays here, we can be sure we're always getting the array, right, has the max score, right, within that size of array. Yeah, and then we just follow that greedy approach to get our answer. Cool. I think I would stop here, and thank you for watching this video, guys, and stay tuned, and see you guys soon. Bye bye.